we can solve this thing and determine it. Yes, sir.
Total is the PO2 pressure, right? That's the total pressure. And the ambient
No, in
is
this case, it's the pressure you're measuring
on the inlet.
in the tailpipe.
Oh,
But it's still a dynamic
It's
pressure,
a
plus
dynamic
pressure, yes.
so it's,
Total. You know, now you're blowing on that air a lot faster, okay? So you put that probe in the tailpipe and you do this, and it works pretty well, okay? A lot of airplanes, particularly older jet engines that weren't fans, that were just pure turbojets, most of them use this kind of a thrust indication. Was measuring a lot of them would just measure this number, but others would make the comparison since they had, they'd get that ratio since they were on board, and you could plot that up and then, get the thrust of that the engine's producing, at least the gross thrust. Well, a similar set of equations, once you get that standing shock wave in the nozzle, now we've got the choke case, and so we have a set of equations for it. Notice that they're a little bit simpler than the others. Pressure of the exit, total pressure again, okay, through there. Velocities, temperatures, and this is gross thrust here, typo. Area of the exit. Again, the same kind of equation we had before. Ambient pressure. Then if we apply our pressure ratio to the whole thing, we get this equation, and we can, assuming that gamma is 1.33 for fluid elevated temperatures, then the equation reduces to a real simple one, where again, pressure sea level, we know the area of the exit, assuming this is not an afterburning engine that has all the pedals and all of that sort of thing, okay? And here's our pressure ratio again. So it doesn't matter, we can use pressure ratio then for either the choked or the unchoked case and determine the thrust. Okay, again, this is for, and what happens, the float chokes at about a pressure ratio of about 1.85, something like that. You develop the shock wave, the standing normal shock wave in the exit. Now, someplace in a jet engine, you're going to have, in the exhaust nozzle, you're going to have a standing shock wave. You say, wait a minute, that's only sonic. How do these things go supersonic? Converging, diverging nozzle. Okay, nozzle converges, there's your normal shock wave, it diverges, and then you start getting other shock waves that are going faster. And so you can, SR-71, we heard some, last week we heard some presentation on the SR-71, 3.2 Mach, requires 3 states to turn around in. Okay.
and if you get lost, you get lost.
And if you get lost, you're really lost.
If you get lost, just go around the world.
And the other thing I learned about it, one of the presentations was that at night, daytime, flying essentially visual references, okay, wasn't a problem. But when they flew at night, up near the space, you didn't have the references were not good, and they had a tendency to overbank and lose control of the airplane. And so they put a laser line across the thing to give the pilots good peripheral vision cues. Rather interesting. I've been wanting to do that sort of thing anyway, just for light airplanes, because when you're flying instruments, you know, you go from a world here that you've got lots of good references and your eyeball is good. A lot of folks don't realize this. Human eye is really good as far as sensing changes. Quarter degree. Think about that. A quarter of a degree. That's hardly nothing. But you take that giant horizon and you shrink it to a 3-inch instrument, all of your good references have went away. You may have a 5-degree change before you even notice it. You know, and that's what they were suffering in the SR-71. But anyway, I diverge here. This is, you know, this is for the thing, and what you'll find if you calibrate this thing, we'll talk about that a little more in a minute. Well, those equations are based on one-dimensional isentropic flow. That's not an actual case. So to correct for non-ideal conditions, we add a factor called the thrust coefficient. Now, we're very good in engineering about coming up with fudge factors. Okay? When our simple-minded theory doesn't work out right, in goes a coefficient. Okay? In goes a coefficient, and here it is, okay? This thing is not defined. We have to actually determine what that is from a real test, okay? So here are the two equations with our fudge factor thrown in, all right? So now how do we determine that? Well, one method's called the jet flow method, and it's based on those two equations. And we measure, what we do is we will put the airplane on a thrust stand. And we tie it down to this stand, and this stand is movable and has strain gauges, which we can tell how much force is being generated. And we run it at various power settings. And so we know what the left-hand side of that equation is then. We have the right-hand side except for the thrust coefficient, right? And the difference between the two becomes our thrust coefficient. Now, everybody doesn't have one of those. However, several years ago, I had a project that had a little powered lift airplane called the Jetwing. Actually, it was an upper surface blowing single engine jet airplane. And it had been in the full scale 40 by 80 tunnel out at Ames. And with the air off in the tunnel, they had actually measured the thrust on the tunnel steam and had a good idea on the thrust. But this had been some time before I got the airplane. So I wanted to make sure that, the thrust measurement in the tunnel was still valid. So what we did, we had a ramp that had a slope to it and tie down places on the ramp. The ramp had about a 5-degree slope. So we tied the airplane to the ground. Now, the other nice thing about this was the exhaust nozzles were on the wing, okay? Nothing came out the table. All the flow came and was ducted into Y ducts and blew over upper surface of the wing. There was a ground handling hole in the airplane where we slid a bar in. It was a tail dragger. You don't see many tail wheel jets, but this was a tail wheel jet. And we could move it around, but that bar made a nice place to attach cables, which were tied to a ground through a load cell. The fact that we were on a slope gave us a preload and got rid of any wheel friction. Okay, so we were able to run the engine at various power settings. I had a student standing off the side so he didn't get blown away with a pair of binoculars looking at the load cell, okay? And he was writing the numbers down there. I was writing the numbers down in the cockpit, what we would set for various things. And we were able to calibrate it, and amazingly, the data fell right on top of the 40 by 80 tunnel data. Okay, so it is possible to do these things without having, you know, the Air Force out of Edwards has this nice movable platform you can taxi the airplane up on and tie it down and do this. Well, everybody doesn't have one of those. And so, you know, you can do your own. If you've got a nice slope ramp, why you can, you know, you can sometimes work these things out. And this one worked very well, and, you know, able to give some of my students some real life kind of experiences measuring jet thrust. So we determined that measuring the thrust is a function of engine pressure ratio on the ground, and a static calibration and plotted as a function of the engine pressure ratio, and that's shown in this next figure. And so here's our thrust coefficient in percent, okay? And notice that it goes up, you know, and then up there as it gets close to 100%, it kind of leans over, and of course the problem is finding where that break in the curve is. Because again, we're tied to the ground, right? We can't get as much thrust as we can in flight. In flight, we're operating, you know, at much higher pressure ratios. So since we can't get those high pressure ratios, we have to extrapolate them to flight pressure ratio values, and of course that's a source of error. Engine manufacturers try to do this, and it's probably one of the least accurate methods since it doesn't account for install losses, because once you put an engine or of any kind, jet or recip, into an airframe, you have install losses. You know, they can put it on a test stand and it'll produce so much power or thrust, depending on what kind of engine it is. But then, we take it and we install it in an airplane. Well, depending on, for instance, a jet engine, depending on the inlet design is very important. For instance, that SR-71 I was talking about had a spike that at very high speed, getting the so-called shock on the lip, as they call it, okay? You have a shock wave from the tip of that spike going back, and it stands right on the lip of the inlet. That's where you want it. If it goes in the inlet and swallows the shock, you have what's called an inlet unstart, and all of a sudden, about 2/3 of your thrust goes away. In fact, that happened, I think that happened to Daryl Grinemeyer in one of the SRs, and he ended up sideways. One of the few guys who survived that kind of an event. You know, it only happened on one inlet. So, you know, here are these two engines way out there, you know, and all of a sudden you lose 2/3 of your thrust on this one, say, and, all of a sudden you're sideways at Mach 3.
Is that the reason why it's moving?
Yes. Yes, that's the reason they have to translate, because as you accelerate, you want to keep that shock wave on that inlet lip, so that spike has to move back and forth. In fact, during the old days, people used to go, this was during the Cold War, people would go to the Paris Air Show and see the Russian jets that had fixed spikes and measure the angle. That tells you what the max Mach is. Okay? So, guys with their cameras, taking pictures, going back and measuring these angles to determine what the maximum Mach number was,
What did it determine to be? Mach 3 or 2?
Yeah, I think they had some 2.5 kinds of airplane, maybe, back in those days. So it's important to keep that the so-called shock on the lip, as they call it, because an engine can only use subsonic flow. So you have to, if you're doing Mach 3, you have to slow that Mach 3 flow down to subsonic before it goes into the engine. So you have a whole bunch of shock waves inside that inlet, and it's important to have the one on the lip to start that whole process out, and then eventually you go through a normal shock wave into the inlet or into the engine face. If it swallows the shocks, it isn't going to run very well. So anyway, that's when we get into real high-speed flight, you have to deal with those kinds of things. Well, we said that engine manufacturers' data, was primarily calculated. Now, if you go down to West Palm, Pratt & Whitney has a big test facility down there out with the alligators and what have you, where they run these engines on stands to try to get some of this data. The wind tunnel calibration, I was telling you about the Arnold Center. Essentially, all they do there, these big wind tunnels, they can put the inlet on the front of the engine. They have a correct tailpipe and all of that sort of stuff, so they can actually put these engines in these big tunnels and run them at those kinds of speeds. But if you live within about 5 miles of that place, you can hear them running in the middle of the night. Okay. Well, if that's accurate, it costs a lot of money because they operate those big tunnels. And the other thing they do, they will take the engine inlet and what have you and do the test in the tunnel and then ship it out to Edwards to be put on test airplanes to try to work this business of getting accurate. Well, expensive, normally only available for government projects, for us taxpayers to pay for. The French developed a method called the climb performance method. I put it in here just to, what it does, it takes the jet flow values for the thrust coefficient and extends them up to through where you can account for afterburners and those kinds of things. And it's really kind of an extension of the jet flow method. I don't know how many folks are using this these days, or if anybody is, but we essentially say with this method that the thrust values and what have you at low altitudes are good, so we can measure things at low altitude, and then that these things are accurate at speeds for best rate of climb, and then we compare the thrust under those conditions to the thrust at a higher altitude, at the same airspeed and referred engine speed, okay? This is the engine speed over the square root of the temperature ratio. Same temperature ratio you've been dealing with for everything else. That's kind of nice about flight test. We use a lot of those same values for a bunch of things, okay? And this is called the referred engine speed. Actually, it's a corrected speed that you can, good for a whole bunch of altitudes. And when we do that, we can determine then if there's a change in the thrust coefficient. And here are the equations that do that. We use the same climb airspeed and the same referred engine speed. We can assume that the inlet drag is going to be the same at both altitudes. Okay, and then if we measure the rates of climb at both altitudes and compare the net thrust at both altitudes using the thrust horsepower and excess equation, okay, where we have, and the H and the L in these terms mean high and low, okay? So net thrust high, net thrust low, drag high, drag low, mass at high altitude, airplane weight and those kinds of things, mass at low altitude, two rates of climb, high and low, and then the airspeeds. And from that, we can tell if there is a change in the coefficient. We can write that previous equation like this. And in a climb, the first term decreases with increasing altitude, and the second term changes only slightly. If the rate of climb ratio is greater than 0.5, it can be considered at second order and calculated. And it provides data on the thrust coefficient changes with altitude and can be used to determine the thrust increased with afterburner operation, which a lot of times we can't do. We can't operate an afterburner static for very long because of the heat the thing generates. You melt the tail of the airplane. So, in this case, in flight, you can operate it for a longer period to measure things. Okay, questions? One of the things I didn't cover here is fan engines. Generally, fan engines, the majority of the mass flow is created by the fan. And so in fan engines, we normally use N1, which is the fan speed. And so power settings for the pilot, he sets an N1 value, and from that he has some idea as to what his thrust is going to be. We used, on this little airplane I was telling you about, we used both the fan speed method and the pressure ratio out of the nozzles. In fact, one nozzle was fan air, the other nozzle was core exhaust. We made the comparison between the fan speed thrust and the pressure ratio thrust, and they actually compared very well on that engine. It did not have a real big bypass, although it was a good engine. Questions? It's lunchtime.